Hello everyone, my name is Jason Lee. I'm a partner group developer manager from WebXT platform team. It's my great pleasure to be here to join the Microsoft Research Summit with Knut.
And I'm Knut. I'm a distinguished engineer working on the Bing search engine together with Jason, and we will talk to you about vector matching in Bing. So Bing operates a hybrid between classical information retrieval and semantic vector-based matching. We continuously build an inverted index of the entire content of several hundred billion pages. In parallel, we also index a semantic vector space. As queries arrive, we parse and convert them into two main formats. User queries are kind of semi-natural in language, means some type real questions, other list keywords they're looking for. Some even use our operators to kind of indicate what they think is important. So we take those queries, we parse them into a executable parse tree. In parallel, we also use a model to generate vectors of that query in a semantic space. Now, at the next step, we send the query tree and the vector in parallel to two different indices. The first one uses a posting list index. This is a classic information retrieval system for all the documents and all the hundreds of billions of documents. They have pre-computed scores for some of the terms. This is a massive parallelized intersection and matching phase of all these posting lists. This comes out with a candidate result set based on the classical scoring system. So in parallel, we also use the vector and we do an approximate nearest neighbor matching in a massive semantic space. Each of the hundreds of billions of documents is also represented in the vector space, and we find the documents that are nearest in this space to the vector. Both these results are finally combined into a ranking system, and this is kind of the holy grail of any search engine and Bing as well. These results are combined. We use a combination of classical information retrieval things like BM25F and the vector distance, I mean the similarity in the vector space. These are all kind of coming together in a universal space, so we compute the merged rank of that, and that's kind of the combined result set. Bing also uses additional signals like user location, things on how we compose the whole page result set. Sometimes these come back and we do a third level re-ranking or even a fourth level re-ranking, but that's all done on the combined set of results. So now let's look at the challenge of the vector space matching. Jason.
Thank you very much, Knut. The Bing's vector index is codenamed as space V. What differentiates space V from many other vector index is its scale. We need to host hundreds of billions of vectors. Each vector could have hundreds of dimensions in order to reach our required precision. The search with this gigantic vector dataset need to complete in single-digit millisecond. And every day, we need to change tens of billions of ranking vectors without downtime. So how could we achieve that? We build a hybrid memory and SSD index we call span index. In memory, we have a coarse-grained navigating index. We partition the vector space into subspaces with balanced k-means tree, and each subspace is represented by a centroid. The uncompressed dataset is stored in the SSD in a format similar to the posting list. Essentially, the vectors close to a centroid are packed together as a sequence of 4K pages, such that when we need to load a subspace, we only need to do one or two SSD reads. We also use a relative neighbor of the graph rules to add a vector into multiple subspaces to avoid the classic ANH problem. And because each query we need to load tons of vectors from SSD, we develop a block I/O mechanism to bypass the file system to maximize the SSD throughput. With span index, the search becomes straightforward. We firstly find top-n candidate subspaces, from the in-memory index. We then load them from SSD to memory for another level of fine-grained search we call re-ranking in order to achieve our required precision. The span and block I/O techniques are joint effort with MSR Asia. For algorithm details, please take a look at our span paper, which is submitted to this year's NIPS conference. The Bing's vector index and its technique are used in many scenarios, like web search, multimedia search, feed recommendation, contextual ranking, etc. Hence, how to train vector with a multimodal in a combined vector space is a very active research area. And with the deep learning model become more and more powerful, especially with the attention mechanism, we want the vector to carry more information with higher dimension. Then how to efficiently store high dimension vectors, yet still achieving good accuracy, is also a frontier to explore. Scaling out and scaling up are another hot research area. For example, we need to lift the space-V vector search throughput in magnitude when we considering scenario like Windows feed recommendation, which pose a unique challenge for SSD-based graph index. Now get back to you, Knut.
Yeah, finally, as we mentioned earlier in the presentation, we have a parallel search system. We have the classical information retrieval and the vector space model. In the classic space, we find ourselves more and more in moving from the 1970s research paper on how to invert the index into a place where we use deep learning models to select and pre-compute pieces of the index. In many ways, we're kind of getting into the way of learning to index. This has been particularly interesting as we scale up the number of documents, the number of queries, and some of the new scenarios that Jason just mentioned. One thing that stands out interesting, though, is if you recall those two paths, we really don't want these two paths to give us the same candidates. We actually want them to give us different candidates, broadening the space of where we find the matches. So an interesting, almost philosophical problem space is like, is there a combined model that generates a very efficient vector space semantic search, but also a model that we can invert or extract the negatives from? Things that we should really put into the classic index. So can we learn how to do the semantic vector space and the classic index by a single fusion model? That is an interesting problem that we keep on pondering into in many settings. So thank you all for listening, and that's it for us.